Okay, I have to confess I'm a little bit in a conflict because several of you have approached me and said, if you talk about the universe, hopefully it's not too much of a PhD talk. So then I felt, of course, I have to dumb it down. But then I talked to Miss Lynn, our religious education teacher, and so some of the kids will be sitting in, so now I have to ramp it up again. Okay, we'll start with a few experiments. Just to illustrate the method of science and some fundamental laws of nature that we will later revisit when we talk about the universe. Get the props here. Okay, the first is a pendulum, obviously. Most of you have probably experienced that. And the first realization we have is nothing really happens unless we add something to it, and that is energy. So I add some energy to this right now by lifting this up. Force times distance, this is what we call a potential energy or a height energy, if you wish. And if I let go now, of course, we see the pendulum moving. And this is an example where the height energy is turned into speed energy as this moves to the bottom at the maximum speed. And then it climbs back up on the other side, turning the speed energy back into height energy, right? And so eventually, of course, it comes to a standstill. So some of the energy is actually lost here through some friction and this screw that's moving through the air that creates some turbulence, and eventually that turns into a little bit higher temperature in the room. So anyway, the lesson learned is nothing happens until we add some energy. And secondly, what this is an example of is that energy cannot be created or destroyed, it just changes form. We have height energy that turns into speed energy as it goes at the bottom, and then it turns back into height energy as it swings up on the other side. And so the total of those energies always remains constant, which means that if you let go here and measure the height of this, with a ruler, and then let go and measure the height at the other end, we can expect the very same thing. So that's called conservation of energy, and it's a fundamental law of nature, which basically said, it's like a bank account. If we take energy out, we reduce the energy in that bank account, and then we have to fill it back up with energy if you want to bring it back up to its original state. So that's what is called the First Law of Thermodynamics, which is basically the balance of energies that we have around us, and that's a very universal law that happens all over the universe. Now the second law of thermodynamics deals with something that we've already seen a little bit here, namely the fact that this pendulum doesn't come all the way back up to the height that we let it go of. So there's something lost here in the friction and the warmth, and that gets into the room then as turbulence of the air and so on. And that part we cannot recover, so it's lost. And we'll have a little similar demonstration here with these two fluids. This is just water, and this used to be Aunt Nellie's pickles or Aunt Nellie's red beets, right? So I ate the beets, but this is the juice that's left over. And I have a syringe here that I'm going to fill up with that juice, and then very carefully we'll try to add that to the water. And I try to do that very gently so the fluid stays separate. So I'm just squeezing it in there very gently to the bottom. Okay, put the cap back on. And you can already see it really doesn't want to stay totally separated. If you carefully lift it up, then there's a slight separation, maybe because the one is a little bit heavier than the other. Is that the wrong size? I didn't realize that there are different sizes. There we go. Anyway, it's a little bit dark at the bottom, if you can see that, and the water is on top. So if it's a matter of being maybe the juice is a little heavier than the water, let's turn it around and see if it goes to the bottom. Doesn't really happen, right? We have pink everywhere. Mm-hmm. In other words, it's perfectly mixed. The juice particles have spread as much as possible in that fluid. And that's another tendency of the universe. Think of a scrambled egg. It's much easier to scramble an egg and you have mush than do the reverse, trying to make mush into an egg again. That's very hard to do. Right? Now inside the hen, of course, that's done, right? The hen makes the egg grow, and so that's what life does. Life assembles sophisticated things. But the non-living world, things tend to crumble. You know that from your personal life experience. Things fall apart. Right? So anyway, leave it with that as an introduction to two major trends that happen in the universe. One, of course, being with energy and the change of energy, but the other one, and that has to do also with building complexity. It takes energy to make things that are sophisticated. If you talk about complex systems, think of like the old cities like London. They have a lot of one-way streets. That's a complicated system, and if you drive long enough in London, you eventually figure it out. What are one-way streets and what are two-way streets. But imagine that one-way signs flip around depending on the traffic amount. Now you have a complex system, right? So anyway, that's how many things are in nature also. So let's move that away. Actually, I'm getting a little dry here in my throat. It's truly just juice, don't put ink in my body. Right? Okay, let's do this. I thought I'd start out with a quick review of what we call the scientific revolution. Just some examples of some scientists that got this whole thing in motion. It's only about 400 years old, right? So keep that in mind in terms of the age of the universe. That's basically nothing. Our Western society pretty much started with some of the Greek philosophers who were trying to figure out what works in the universe. And they started out with trying to solve geometric puzzles. Probably all of you are familiar with the Pythagorean theorem that says that the square of the long side of a right triangle is the sum equal to the sum of the two shorter sides. That's shown here, and so on. I'm not going to go into many details here. Many of the people, of our history have looked at the heavens and saw that there was some regular motion there, and they tried to figure out, how those stars move, and also tried to make predictions. And for over 1,000 years, the worldview was accepted based on what this gentleman had written and published. He lived basically around 100 years after the birth of Christ, and he was a Roman citizen, but it was Greek by descent, and lived in Alexandria, which is, of course, in the Middle East, and that was also a center of learning and education. So he had a lot of data from astronomers that looked at the skies. So he was very much known in his times and later because he published this almanac which had stars, their locations, their coordinates and so on, and it was based on what we call a geocentric system. You see here the Earth being in the center, and some of the spheres that they envisioned. Noticed that with the Earth in the center, they thought the second thing, or closest thing, was the Moon, of course. Then we have Mercury, Venus, the Sun, then Mars, Jupiter, Saturn, and that was the planets they knew at the time. Actually, they didn't realize that the planets were spheres like the Earth. They thought they were stars. You know, they were moving stars, as opposed to the fixed stars at the end of the. Notice also they always had to justify a kind of religious impulses there. So the outer sphere is the heavenly home of God and all the chosen ones. You know, that is reflected in that chart. Okay, actually the fact that some of the stars are wandering, you know, they go at times they go back and then forward again. They try to resolve that by having this strange combination of rotating spheres. Actually, the Earth is a little bit off-center there, and there's a total sphere that Ptolemaeus envisioned, and then a planet would then have its own little rotating sphere, and that if you envision this thing moving backwards in this fashion, then you see some retrograde motion at times that can be constructed with that. So kind of a weird way to look at the world, but that was just an attempt to create that kind of motion that we see by observing the stars. This was a Polish astronomer by the name of Nicolaus Copernicus, who had some doubts with this geocentric system, and he actually proposed that the sun is in the center, just from his observations. But he was afraid to publish that until friends urged him to do so at the end of his life, and that then eventually got, the news got around that possibly the sun could be in the center. So that is our heliocentric system, and you see that now the sun is in the center, then we have Mercury, Venus, and then the Earth with the moon circling around the Earth. It's still all full circles, so you know, when they tried to make predictions with that, it matched the actual position of the stars much better, but there were still some significant errors that weren't quite resolved with that. Of course, you know, the church was trying to suppress this kind of view because the Earth was no longer in the center, and there are apparently some passages in the Bible that say, you know, that the Earth should be the center of the universe. Now, this Copernican view with the sun in the center gives a more elegant explanation why the stars move retrograde. So if you see the sun there in the center, then that inner circle with the T's, that stands for Terra, that is the Earth, going also faster than an outer planet, for example, Jupiter, that would be on this outer circle. You see then at point 1, 2, 3, and 4, the Earth is, so to speak, passing the planet Jupiter on the inside, and then from the viewpoint of the Earth against the fixed star sphere of the background, it looks like Jupiter is at first moving forward from A1 to A2, then backtracking to A3, A4, and then catching up and going A5 again. So this heliocentric view gave an elegant explanation for this wandering of the stars that we see happening in the real world. But again, we still have circular motion that was trying to please the church, until Johannes Kepler came along. He was a German-born mathematician, really, who got together with Tycho Brahe, who was a Danish nobleman who had very meticulous data of the stars. And so by using Tycho Brahe's data, Johannes Kepler came up with figuring out his famous law about planetary motion. And so this illustrates it a little bit. You see two planets here and their respective ellipses. And Kepler's law basically said that the sun is in one of the foci of the ellipse, and that the line between the planet and the sun sweeps over the same areas at equal intervals of time, and then the total time for revolution, around the sun, the square of the total time is equal or is proportional to the cube of the major axis of the ellipse. So it gets a little bit mathematical here, but that seems to be the way the universe talks to us. We formulate, we actually take data first. That's what we saw on the pendulum by measuring the height and the speed. And then out of the data, we try to figure out how they relate to each other, and then we come up with equations. And then we try to make predictions. And if the universe meets our predictions, then that's the answer, right? So the numbers and the parameters are given then. Galileo Galilei was an Italian scientist who did all kinds of interesting experiments. One of his most famous was dropping two spheres from the crooked tower in Pisa, right? That's a perfect experimental place. And he found out that if you have a wooden sphere and a metal sphere, obviously the metal one being much heavier, they still both fall at the same speed. And that experiment was repeated by astronaut David Scott on Apollo 15 in 1971, where he actually did a hammer and an eagle feather drop in the gravity of the moon. There's no air on the moon, so there was no air resistance that would slow the feather down. So they actually did drop at the same speed. So that's one of the fundamental insights they had there in what gravity does to a mass. And then, of course, 100 years later, Sir Newton came along and figured from the data of Kepler and Galilei and others, he figured out that you can combine those positions of the stars or the planets with some forces. And now we're talking physics. It's no longer pure mathematics trying to describe the path. We now have a cause and effect, right? A force that starts to accelerate a mass. And so that's the famous equation F equals ma. So here's one PhD equation. That's the Newton's law expressed in vector. So that little arrow over the F means the force is not just given by its magnitude, but also has a direction. So when we have a force, it causes an acceleration in the direction of the force. And that little sigma there in front of the force, that simply means we not only look at one force, we may have several forces acting on a body, and we just need to find out what is the resultant force, the vector sum of all these forces. So that's the only PhD equation I have here, so there won't be any more. Okay, that's Newton's law of gravity, and that's his famous story that he actually had that idea when he sat under a tree contemplating like Buddha, but then an apple fell on his head and then he had that insight. So that may be a legend, but anyway, this law basically says the magnitude of this attracting force of gravity is proportional to the two masses that are involved, and the square of their respective centers of gravity is distance. So with those laws, he could exactly predict the location of the of the planets, and that, of course, was part of the scientific revolution that now was out there. So that's the difference between a scientific story and, say, a fairy tale or some other story that somebody tells. In science, we come up with a story, but we then give it to the world and say, check it out, do experiments. And if it withstands the guillotine of the experiment, then it becomes a theory, and it explains how our universe works. Albert Einstein, again, he is most famous for this simple formula, the equivalence of energy is mass times the square of the speed of light, and that's a very large number. And of course we have seen the result of that law of nature in the atomic bomb, where you can transform a little mass into a huge energy. It goes the other way around too. When the universe started to form, it transformed energy into masses, and then if that wouldn't be the case, we wouldn't be here today. Right? Okay, so there's much more to Albert Einstein, but he, for example, he saw that Newton's equation, or Newton's law of gravity, couldn't stand the way it was, because it would imply that if the sun collapses right now, we would immediately feel a jolt here on planet Earth. And Einstein found that the speed of light is also the maximum speed that any type of information could travel in the universe. And so it would take about 8 minutes, for that information that the sun collapsed to get to the Earth. So there's no immediate, shaking of the Earth if the sun would collapse. So he came up with a total new way of explaining gravity, and again, that would be too much PhD stuff to go into the details of that, but he calls it the warping of the space-time continuum, and that's illustrated by this network, if you look at it here. So it's a little bit like that coin machine in the Hands-On Science Center that has a funnel shape. If you drop a coin there, it spirals around, and eventually, of course, disappears in the hole, because the Hands-On Science Center wants to make some money. But it's an analogy to the space-time warping that is caused by a heavy mass like the sun. So if the sun would disappear, then this warping would unravel at the speed of light, and we indeed would feel that 8 minutes later here on planet Earth. So Einstein suggested to test his theory on what is called the precession of the perihelion of the orbit of Mercury. So that one, you see an elliptical orbit here of the planet Mercury, and that, of course, can be explained with Newton's law and Kepler, but what cannot be explained with those laws is the gradual rotation of this whole orbit over time, and that is actually the case. It's about 4 centimeters a year, so it takes a lot of high-tech instrumentation to actually even measure this effect. But we are in a position nowadays that we can measure such small changes, and that proves that Einstein is true, and we had to give up on Newton, basically. There are ways to make Newton's equation work, but I just want to demonstrate this issue of science. We figure something out, it works for a while, then we find more data that tend to not agree with it, so we have to come up with a new theory, and hopefully that one works. This is the case here in this example. Okay, let's go to big history after this little excursus on history of science. So we have these 2 major trends in the universe. One is this decreasing complexity, breaking an egg, making mush, tasty mush, but it's mush, right? On the other hand, this trend of life, basically, to get to ever-increasing sophistication, more complexity in the world. So it seems like the universe does allow some increasing complexity, but the general tendency is for it to go to lower complexity, to disorder, and those things that are expressed by the second law of thermodynamics. So how can we have increasing complexity? It takes special conditions. One of the scientists called it the Goldilocks conditions, right? When we have things being just right in certain pockets of the universe, then we can get a boost of complexity. And the scientists who put this big history together, they talk about thresholds. So we have a certain threshold, and then we get more complexity growing out of that. It tends to be more fragile each time we get to such a threshold and increasing complexity, but it does happen. Okay, so let's wind back the clock. And this is kind of through backward engineering from all the laws of nature that we know. You know, we think we can figure out how long it took for things to develop. And here's the number, 13.7 billion years. That's when the Big Bang is assumed to be have happened. So let's just envision what was there. Envision completely nothing. No time, no space, and the whole thing cubed. That was the universe before the Big Bang. And then, bang, all of a sudden, a universe appears. It is incredibly dense. It's very tiny at first, smaller than an atom, but it has everything in it that we have now in it, basically. It expands rapidly, like busting at the seams, so to speak. And then distinct features start to emerge, like strong and weak nuclear force. Those are forces that we know now that happen inside of an atom that hold it basically together, the core. But then we also have the larger forces, not in magnitude larger, but in range larger, the electromagnetic forces. You know, kids, you know, when you put a north pole and the south pole of a magnet together, they attract each other. When you put a north and north or south and south together, they repel each other, right? The same holds for electric charges. Positive repel, negative also repel, but positive and negative attract. So that's electromagnetic forces, and then we have gravity. Gravity is the weakest force, but it's the queen of the forces because it penetrates everything. Gravity is everywhere. We can't shield it. You know, the electromagnetic forces we can, you know, cancel with opposite forces, but gravity is everywhere. So anyway, all this happened within 1 second, right? Within 1 second of the universe starting. Some energy congeals to form matter. We see some protons actually being emerging. And NASA has a nice diagram that kind of tries to illustrate what was happening. So we have this Big Bang here happening at first, and then after some protons form, we enter the dark age of the universe. There's nothing lighting yet, there's no light, but we have at least some mass particles floating around. And eventually they capture some electrons and form atoms. So this happens 380,000 years later. That's twice as long as you know, we consider humans living on the planet here. Okay, now that originally that universe was kind of boring. You know, you had just some helium, that's the simplest atom, and some hydrogen, hydrogen and helium atoms, so those are very simple atoms. And there's not much else. In a sense, it's almost perfect mush, if you want to consider it that way. But newer satellite experiments have shown that there's a subtle difference in that background temperature of the universe, which is illustrated in this picture. So the blue areas are just thousandths of a degree colder than the red areas. So you have very subtle differences in the universe, and that's where gravity starts working. When you have just a slight difference in density of matter, then gravity starts doing its work. So it's pulling more matter in it. And that's the thing with gravity. The more stuff you have, the more it pulls. And that's what happened then to this universe, which was originally very much just all this distributed mass, but then in pockets of it, it started congealing. And against this trend of expanding, that's the thing. You have on one hand the universe expanding, so matter gets thinner, so to speak, more apart. But then you have these pockets where gravity is overpowering this expansion trend and pulls things together. So as this happens and the matter gets closer and closer together, the temperature rises, the pressure gets up, and then high pressure and a critical temperature of about 10,000 degrees. It doesn't terribly matter what units you use, usually Kelvin. Protons fuse, huge release of energy, and now we have light spitting out. In other words, stars are born. That's considered the second threshold. And stars are popping up everywhere. The universe lights up, so to speak, and we have stars building up everywhere, billions of them. And some of them form these galaxies, which are the largest objects that we know in space nowadays. And again, there are billions of them spread all through the universe. Now, some large stars, when they die, there's so much pressure, so much temperature inside that more nuclear cores fuse together and form the elements. So this is the birth of all the elements that we know now in chemistry, the periodic table of elements. That was then basically forged in these big stars when they die. And that's called a supernova, when the star finally explodes and spews out all that matter into the universe. So now the universe is much more interesting. We have different types of atoms, more material, and we have more sophistication. And about 4.5 billion years ago, some of those matters clumped up and formed our solar system. So we have the sun, then Mercury, Venus, Earth, with the moon there on the side, and then Mars, and so it goes on. The planets here in these pictures are drawn approximately to size, but the distances, of course, are compressed, so this is not to scale. Anyway, so that we think happened about 4.5 billion years ago. And now we look on what happened on planet Earth, namely the emergence of life. What are the Goldilocks conditions for life to emerge? First of all, we need energy. Remember the pendulum, if no energy, nothing happens. But also we need diverse chemical elements. And fortunately, planet Earth had a plethora of chemical elements. It was now just a matter of getting them together. And that happened typically at the bottom of the oceans. So the first issue is we do have oceans. The planet is right at the right distance from the sun, so we can have oceans rather than having everything evaporate or freeze. It could have been an ice planet if it's further out. But so we do have liquids, and the Earth crust is still cracking sometimes, so the heat comes from the bottom, and then with all the chemical elements, we have a primordial soup of all kinds of chemics going on. And so now these, by happenstance, at first form more complex molecules. But anyway, in order for this to happen, we need to have basically the requirement of liquids. It happens so that when we look at gases, the atoms or molecules move so fast that they don't really link up very well. On the other hand, if we are in a crystal, in a solid, the atoms, they are stuck, they can't move. So that's the beauty of liquids. You know, the molecules can cruise, they can cuddle, they can link up. So it's what causes the possibility of large molecules to form. And those are necessary for complex life functions. And here life comes up with another trick. Rather than stabilizing the individual complex molecules, which naturally are somewhat fragile, you know, if it gets a little bit too hot, they break apart, or there are other reasons for them not being together. So rather than saving the individual complex structures, Mother Nature comes up with this concept of building a template, changing the information. And that's what we call DNA. DNAs are very complex structures, but they have a pattern. And so here, this is what life does. Rather than waiting for a chance to link up with certain molecules, they grab molecules and then assemble their own kind. So reproduction is born. And that's what life is reproducing certain complex structures on a molecular level. So the copyright of life starts filling the oceans now. The DNA gets reproduced and we have all this life. Now one of the beauties of the DNA reproduction is, oddly enough, that it occasionally has a flaw. That's shown here by this red bar in the helix of the DNA. And what that means, of course, we have a flawed piece of life structure, but occasionally that flaw actually makes a better piece of life. So we have a way of learning now. You know, we try different things and some work better than others. And that's the history of evolution. We have originally, for the better part of 4 billion years, a single cell life, you know, being part of the ocean structure. And there's a lot of changing and variety inside of these single cellars, but it takes a while before cells, you know, use multiple cellular organisms. That happened about 600 million years ago. In the top left corner, you see multi-cells organism evolve. And then it's almost unstoppable. It keeps going. We get fish, we get plants, land plants, we get insects, first amphibic forms of life, and then of course the dinosaurs. And they ruled the earth for quite a few years, from about 250 million years all the way down to about 65,000 years. And that's when a disaster happened. An asteroid, a pretty large asteroid, hit the Earth somewhere where the Yucatan Insula is right now, or peninsula. And that changed the atmosphere like after a nuclear war, similar like that. So it was very bad news for the dinosaurs. They got extinct. Good news for some of our mammalian ancestors, like the little mouse or others that you see there, who could live in that, in those niches that the dinosaurs left, and so that life flourished. And you probably know the rest. They evolved from, you know, other mammals, and then eventually we arrived at Homo sapiens about 200,000 years ago. Now this is considered another threshold in the complexity of the universe, and here's why. Evolution is awfully slow. I mean, it has some learning, but it's this trial and error method, and it takes generations for new life forms to really evolve and work. But evolution had ended up creating life forms with brains, and brains could learn in real time. The problem is with brains, when the individual life form dies, it takes the experience and knowledge with it. But humans have language. So that allows us to accumulate knowledge, and when the individual dies, the knowledge still exists. We have a history, and we can learn as a collective learning experience. So this is shown in the early history of human migration, multiplied and grew, and then about 500 years ago they started linking up on the whole globe with shipping, of course, and then as technology progressed, with telephones, radio communication, of course nowadays airlines, and the internet. So we an extremely complex system on our planet. And another energy boost occurred with fossil fuels about 200 years ago that gave another boost to the complexity and a interrelated net that we have. So here we are on our precious blue planet. Hopefully we can appreciate how special it is and how fragile it is, giving a comparison with other less complex systems in the universe. And I like to close with something that is not from Mother Nature having revealed to us, but what we as human beings have brought to this planet. And that's subject to another talk.